I'm Marco. I'm the project manager at of Tendermint, of Tendermint Core, that is, not the VFT. And so today we're just going to do an intro to Tendermint. We'll start with kind of the history of it, and then intro to consensus, and then of course the intro to the Tendermint code base, the protocol itself. So kind of how did about me, I guess I'll start. So I'm from Portland, Oregon in Croatia. The product manager, kind of worked in partnerships. I do a lot of coding day in, day out on Tendermint and SDK. Worked on the proof of authority module within Tendermint. Run a validator, and I work on dticket, which is an application that uses the SDK. So the history of Tendermint and Cosmos. So when Ethereum and Bitcoin came out, Jay kind of realized that proof of work wasn't the future, and so then he wrote the first paper for Tendermint, and that's consensus without mining. And this is where we first saw kind of the introduction of proof of stake and a non-proof of work algorithm. Soon after that, Ethan Buckman, the second founder of the company and the ICF, wrote his master thesis on Byzantine fault tolerance in the age of blockchains. And then a couple months after that, Zaki, Jay, and Bucky envisioned Cosmos, the internet of blockchains, and that's what Billy talked about in the last talk, but also the interoperability between blockchains and machines. And then the most recent paper of Tendermint is latest gossip on BFT consensus, and this is done also again with Jay, Bucky, and one of the lead researchers from the Interchain Foundation. This is kind of the most up-to-date paper if you guys want to read it. But then the most recent things that we've been mentioned in, but also a lot of the research has stemmed from the work that was done previously, is something like Hot Stuff. I'm not sure who people here know Hot Stuff, but it's supposed to be the consensus of Libra. And in Hot Stuff, it's kind of like an adaptation of Tendermint BFT. And then in 2019, we had the Cosmos Hub launch, and this happened in March of last year. I believe it was March. And so far, there's been 3 upgrades. It's running smoothly, no major problems. Everyone's happy. And then, of course, Libra. When Libra came out, a lot of the design architecture of the consensus and also of the code base of the protocol has stemmed from Tendermint Core, and like I touched on earlier, how you can interchange with the Cosmos SDK. They have a module called the mission control, where you can essentially put anything on top of Libra itself. So now blockchain consensus. This is kind of an ongoing subject in blockchain, but not only in blockchain, also in distributed computing. And so some of the, so first we'll cover what safety and liveness mean in the blockchain world. So safety is kind of when a single agreed upon chain is the choice rule. And then safety is meant for finality. You can either have probabilistic finality or actual finality. Probabilistic finality are chains like Bitcoin, Ethereum, Zcash, primarily because there's no consensus on the actual transactions. It's just producing blocks. And so liveness comes from responsiveness, when a new transaction is able to be put into a block. But of course, you also have faults. These are difficult to detect in protocol, and so sometimes you have outside of protocol, outside of consensus, mechanisms to track faults, and this can include information withholding, message reordering. This is kind of rare to see, but when it does happen, everyone's kind of all eyes on it because it's actually quite interesting. So the industry consensus outside of blockchain, there's Paxos. Paxos was, the paper was written in 1988. You most likely used it in your day-to-day life and not known about it through Amazon, Google, and Apache Zookeeper. And then soon after that, Raft came out. These are both also BFT consensus algorithms. Raft is used in Kubernetes. I'm not sure if people here know Kubernetes, but the interesting thing about Raft is that it's a leader-based algorithm in which if a leader doesn't send a ping back to the workers, then the workers start proposing themselves to become the leader. So Very seldom does it actually switch, but when it does, it's able to handle faults. And so now we have BFT. So we have async, synchronous, and partial synchronous. The differences between these three are in that async, messages can take as much time as they want to respond. The wording there is kind of off, but when a message is sent or received, the protocol, the machine has, in theory, an infinite amount of time to respond to where the message came from. In asynchronous, they have a finite amount of time. It's not really preferred, primarily because it needs a large number of nodes. It's lockstep execution, and then, of course, attacks are kind of easier to be done. Now, there's a new paper that I actually just read this week on synchronous hot stuff, and this would introduce, in normal BFT, you have the 1/3 can become Byzantine, and sync hot stuff, then it goes up to 50%, and they try to fix these non-preferred rules of synchronous BFT in order to make it somewhat usable, and they're trying to replace stuff like RAP and these other simpler consensus algorithms within data centers. Now, partially synchronous, this is where Tendermint comes in. Paxos and Raptor here, it's kind of a mix of both. You have the option of having an infinite amount of time, but you also have timeouts. It's so the protocol developers have to make assumptions in order to progress to the next round, to the next block. If you have any questions, do ask. So this is kind of how message passing in Byzantine consensus happens. So it's kind of, you have the client that produces the block, and then it broadcasts through all the messages. So here you would have the block proposer. It proposes, it sends it to all the nodes in the network. So in the case of, let's say, the Cosmos Hub, you have 125 validators. And so the block proposer would send the block to each, and then they have to send a message to all the other nodes, because all the other nodes have to actually know that everyone signed, who signed. In Tendermint's case, and in the Cosmos Hub case, you wait for all the votes to come in. And now you have the option of waiting for only 2/3 and then proceeding. This is kind of what Hotstuff aims to do with an extra round, and this brings it into responsiveness, but it's not really preferred at this time because there's still some unknowns. But as you can see, the message complexity grows linearly with the amount of nodes in the network. And so this is the networking aspect of the consensus. And so here, within Tendermint, we have roughly 2 rounds. So you have this would be the block propagation round, and then you have the prepare, and then the commit rounds. And then everyone's signing votes, signing commits within the network. So Tendermint is partially synchronous. Like I touched on, it's 3 stages: block propose, pre-vote, and pre-commit. And then at that time, you have the finalized block. And so I believe there's a question on how does consensus actually come to finality in the previous talk. Well, primarily it's there's a voted upon block by the validators. And once everyone votes on it, it goes into history. Then once it goes into state, then it just becomes final. It cannot be redone unless you have greater than 2/3 of the network. So you have to have roughly 67% of the network to actually be able to attack the network. This is yet to be seen. On a mainnet, there's some experiments on it on low valued chains, which kind of the same, a similar issue in proof of work. If your value is lower, it's actually, if your hash rate is lower, then it's actually quite easy to attack the network. It doesn't matter about your market cap. Today in the proof of stake landscape, Tendermint is actually one of the most used, primarily because of the separation of application and consensus, and this is something that I'll touch on in the next section. So here we have proof of work. Proof of work, the pros are it's very simple to understand. It's just a puzzle, and it's simple to define economic security based on hash rate. But the cons are, of course, it's probabilistic, it has low throughput, high latency, and it's not energy efficient. There has been some work to increase throughput, and then increase throughput, but then of course, as you grow in the network of nodes, you run into the distributed computing problem of more nodes, it becomes slower. There are examples of hybrid consensus algorithms, which separate block propagation and block finality. And so this is something that some networks are doing where they have proof of work to propose the block, and then they have an entire different mechanism to actually try and finalize the block with the validators in the network. So Tendermint's proof of stake, it's actually based on weight, and so essentially you just have to have a certain weight associated with a validator. So you can run proof of authority, you can run proof of stake, and also you can, if you really want to, go back to the Stone Ages in the blockchain world, you can go back to proof of work within Tendermint. It has instant finality, so you are waiting for the block, for the votes to come in to proceed to the next, to proceed to the production of the next block. And this is something that hybrid consensus tries to move away from, primarily because they believe it will speed up, but then it opens up a whole can of worms. So it's efficiently support lifelines. And then the interesting thing about the protocol itself is it shifts the concerns of the security concerns to the state machine. So Tendermint is essentially simple. We try to make it as simple as possible. And then the application layer has to make assumptions of how the economics work, how the security works, and this is what has made, in a way, things simpler to develop on Tendermint. But then the biggest con about proof of stake, proof of authority, is you have a whole different area of complexity away from proof of work. So in 2017, I'm not sure if Jepsen is a well-known fuzz testing tool within the distributed computing community, and he did a talk in 2017 about Tendermint and Byzantine fault-tolerant databases, and this included Amazon DB, Google ZB, all these other DBs. And at the end of the talk, and at the end of the testing, they found that Tendermint was one of the only databases to date that actually provided a fully Byzantine fault-tolerant environment. Now, in this sense, when I say database, Tendermint is a blockchain, but at the core, it's a state replication machine. It's a distributed database, and so that's the way we try and view it. We try and kind of stay away from the whole blockchain because, as we talked earlier, when blockchain is finally adopted is when people actually stop talking about it in mainstream. So now we get into the protocol, into the code base essentially. So the ABCI is the application blockchain interface. This allows you to build a state machine in roughly any languages. You have, like Billy touched on earlier, there's the Lotion.js, so you can build out your application entirely in JavaScript. There's Haskell, there's Erlang, there's C, there's Python, there's Go. The only caveat is it has to be deterministic. Of course, you don't really want a non-deterministic state machine to be running a multi-million-dollar application. So what's the main difference between all these others is it's not really your state machine. When you work in Zookeeper, well, you kind of have to adhere to their rules. When you work in Bitcoin, yes, it gives you this one use case, and it gives you this one use case very well, but you can't really do much outside of that. In Ethereum, they introduced smart contracts, but you're limited by the EVM and what the EVM enables you to do. And then you're also limited by the community and how fast you can upgrade. And in all this, you're kind of making workarounds to make your application work. But within Tendermint, we separated the two. So here you have the consensus and networking, and then similar to the Cosmos SDK is the application, and that's actually here. So essentially, you are just communicating and sending only the transactions. At this current point within the protocol, you're only sending transactions to Tendermint, and then Tendermint will create the block, propagate it to the network, and have everyone sign off on it, and then send you back the transactions that were included in the block and that have been finalized. And this kind of simplifies it. In the future, we hope to lift this logic into the application so the application developer can have more control on what they want to do with the block, how they want to structure it. And then of course it brings in, you're able to do stuff in a concurrent manner, speed up, because right now you're just doing, it has to be sequential transaction sending between the ABCI. So now in this area, we're going to the application.
I can stop you a bit on the consensus before we move forward. So how are validators like? How do you become an eligible validator?
In a proof of stake model, so for right now, you would essentially say, hey, go to the network and say, hey, I want to be a validator. And then I have to delegate to myself and say like, okay, I'm willing to put this much money to get into the set, not necessarily the active set, because there's an inactive and active set. Right now, there's, I believe, 168 validators on the Cosmos Hub, but only 125 are actually proposing blocks and finalizing blocks. And then within bonded proof of stake, once you become a validator, then people can delegate their atoms or their token to you. And then you're essentially running the network, and as you grow the amount of delegations you have, this essentially brings up the power you have as a validator. And then this is the power that is the weight that is associated to Tendermint, in which the more weight you have, the higher you are in the validator set.
And the weight is directly tied to how much you stake.
Yeah.
And how much people has put on you to.
Yeah.
And
because others can put
application level.
Yeah.
Application level. So as Marco said,
so this is
concept voting power.
Yeah. So this is kind of shifting the economic concerns to the state machine layer. It's like Tendermint doesn't have a notion of tokens, it doesn't have a notion of voting power, it just has a notion of weight. And so, and similar, like when I was building the proof of authority module for the SDK, all I did was, okay, when you create a node in proof of authority, you initialize a reputation associated with that node, and then you can say as the node progresses in time, as time progresses, the node can gain more reputation because they're doing good stuff to the network. And then if they have a fault, then they can reduce the amount of weight. And it's similar in the Cosmos Hub. It's like when you have a slashing event.
So it's not like staking, like they will be doing it in Ethereum, right? That you have to stake.
Yeah. So in
it's not like that.
In like ETH 2.0.
Yes.
In ETH 2.0, that's
you will have to stake
yeah.
Ethereum.
Yeah.
But it's not like that in Tendermint. It's more like reputation based.
No, it's just that's an example. It's entirely up to the state machine. So it's like with ETH 2.0, you're staking 32 ETH to be a validator. This is essentially the same as the current Cosmos SDK. It's like you have to stake X amount of tokens to get into the active validator set. The proof of authority example is just like an example of
but I understand that the Cosmos Hub right now is running on a Tendermint blockchain, right?
Yeah.
Now, how do you stake to become a validator on that?
So one of these plugins in the Cosmos SDK is called the staking module, and then you say, okay, I want to put this many tokens to this validator, and then once the validator receives those tokens, then it updates the weight that is associated with Tendermint, and then moves them up in the list of validators of Tendermint. And so it's like the validator part is associated to Tendermint, but how the economic concerns of how you increase where the validator is in the list, how much rewards they get, is mostly associated with the application.
Just that the underlying engine, conceptually, like Marco said, it is not tied to any coin or token, concept of coin or token. So fundamentally, each node has a voting power share. You can imagine that you can run a network of four nodes. Each of them has a starting voting power pool of 25% each. And then at the end of each finalization of a block, there is actually an update of the validator set. And so there could be a rearrangement of the voting power. So maybe one node has 5% less and the other one has 5% more. Now the way you actually handle the end blocker and the calculations is actually on the application. So the application might actually, Cosmos and the SDK, you can handle this based on the proof of staking model. So you stake, and according to the delegations, you have more or less voting power, which has some consequences because the more voting power, the more likely you're gonna create blocks. The more likely, actually, it's deterministic. The more blocks you're gonna create, so the more block reward you're gonna get. But in theory, you can run a set of Tendermint nodes for just fundamentally a database application, and you can have a fixed set of validators, and your application will handle the updates of the validator set. And that's how it works, Tendermint level.
Kind of an example of how agnostic and how unlinked it is to blockchain is a couple of years ago, a team took Tendermint and took Kubernetes and actually took Raft out of Kubernetes and put Tendermint in to make it fully Byzantine fault tolerant. And then this was kind of a simple example, and I guess would say an extreme example. If it was adopted, Kubernetes would be entirely Byzantine, partially synchronous, Byzantine fault tolerant with Tendermint. And so it's kind of roughly
like there is the flexibility because you can build your own blockchain with Tendermint, and then you decide yourself, right, how the staking is going to work.
Absolutely.
But then there is this Tendermint-based blockchain, which is running right now, which is running the Cosmos hub.
Yeah.
And that is based on tokens staked, right?
And there is a staking model, so there is a proper economic incentives-based model. But other networks built on Cosmos SDK have their own staking models and their own economic models.
Like, you can even make a proof of work module within an SDK, and then the hash rate is the weight in Tendermint. So it's kind of like giving the freedom to the developer to make their own rules.
I'm giving a little bit extra focus on the Cosmos Hub, right? Because to me, that's the heart of all right, you can have my own blockchains, but really, the whole ecosystem is built on this Cosmos Hub. So that is, in my opinion, from what I'm understanding, is like the heart of your project. Everything goes around it. Am I right or am I wrong?
It's the very first network built on Cosmos SDK. But the Cosmos SDK, for instance, is not even the very first network built on top of Tendermint.
Yeah.
So it's just
it's entirely like the Cosmos Hub, of course, is one example of SDK in a real world use. But essentially, like the idea of the hub and spoke model is that the hub becomes the routing for the traffic of, let's say, this inner blockchain ecosystem. But essentially, like if I'm, let's say, one chain and I know that that chain is very secure, I don't have to make assumptions of like make these random assumptions to say like, okay, this is secure, I'm going to trust this, I'm not going to trust this. Then I can actually just go connect directly to that chain. I don't even have to go through the hub. So essentially, the ecosystem, like the hub could die off, but the ecosystem would still go forward. Like there's now 2 other hubs. One is launched, one is working on their launch, and essentially all the traffic could be routed to them, and no one really goes to the Cosmos hub. Like in today's world, we don't really know what will happen. In the end, what I like to say is that this is all just one big experiment. So of course you have application-specific blockchains, but I mean VMs and smart contracts, they're kind of nice. They're simple. If you build an application, you don't have to worry about your security model. You can just deploy it to a chain that's already existing. That's why Ethereum gained so much adoption. Of course, it's secure. It's mature. The attack surface is smaller because you have just single smart contracts, and it can be scalable. And so, for an example, is we have this project called Ethermint, which is actually a module within the SDK that is just the Ethereum EVM just on top of Tendermint. And so you have EVM, and then you have other projects called something like Cosmos, which is a Wasm-based smart contract VM on top of as a module in SDK. Then you have a JavaScript smart contracting language on top of Tendermint. And so it just kind of opens up a whole new world, and you're able to scale, you're able to not be tied down to the Ethereum and how slow and how slow the Ethereum ecosystem is, because they have so much at risk if something goes wrong. Here, you're able to iterate faster, and you're able to provide optimizations directly for your application. An example like Aragon. Aragon is going to be using the EVM, Ethermint, on top of Tendermint, primarily because they want to get out of Ethereum because it's not as fast as what they need, and they want to just have the freedom to do whatever they want, but not have to rewrite their entire stack. So how is this all possible? And now we use protobuf, and if it's a language that uses protobuf, it's just an encoding format, and then you have files that generates stubs in most languages. Now, when you want to deliver a transaction, of course, you just call deliver transaction and delivers it to Tendermint. Tendermint will create the block. Check.tx is something within the mempool that when you send the transactions and the mempool starts building up, you want to check if that transaction is still valid. And then I guess the most important two aspects of the ABCI in Tendermint is kind of this begin block, end block. Every time a block begins and you want to execute some arbitrary logic, check that this is met to this. If this auction, in the case of an auction, if this auction is over, finalize the transaction. End block, when the block is over, just run some arbitrary logic to just update state, check that these things are valid. You can kind of do whatever you want based on your application. And this is how people are able to build applications on top of it without having to adhere to the Go language. And now this is something state. So Tendermint itself doesn't have knowledge of application-based state. And so this is kind of what also gives you the freedom to take the Cosmos SDK that's been running on Tendermint for, let's say, X amount of years, and switch it out and say, I want to run it on Libra's underlying consensus. I want to run it on Substrate's consensus. It gives you the freedom to do kind of whatever you want. The only thing is that the only state that is aware of is just the weight associated to validators. Other than that, it's kind of your concern. So currently, this is kind of the ABCI ecosystem. For Go, you can build it in process. So in the SDK, it's built together. So when you run the start command for a Cosmos SDK-based application, you start Tendermint on its own. For these other ones, you kind of have to run it out of process, so either in a Docker container or on the server, and then you can do through a Unix socket, or you can communicate through Tendermint through gRPC. So if you're running Tendermint on a server over there and you have your application in a different part of the world or a different server, you can still communicate and finalize your transactions on a different server. From our side, we maintain the Go and Rust ABCIs, but other than that, they're all maintained in the ecosystem and they're all used in production. So now we're going to go a bit into P2P. And so Tendermint uses just normal TCP connections. We haven't gotten to the point of using something like UDP and Quick. So TCP, we communicate, and we are able to build long-lived TCP connections with nodes. Now each node has a global TCP connection to the entire network, but these connections are multiplexed. So you have channels, kind of like what HTTP2 aims to do for HTTP1. You have channels, and then there's priorities on these channels. So you know how to communicate to other nodes, and you can send these connections. You can add prioritization on messages, for example. And then there's peer exchange. So in Ethereum and Substrate, I believe Bitcoin as well, they use a distributed hash table. And so there's always like a central point in the network where there's a table of the entire network of all the nodes that are existing in the network. And then kind of to connect to the network, you just kind of point your node to that table, to the nodes that have those tables, and then you get the entire network on one fell swoop. We kind of do a different aspect. We do peer exchange. And so you actually communicate with peers, to get addresses of different nodes to connect to. And so essentially, this goes into the kind of different types of nodes in the network. You have a seed node. A seed node is is primarily just a P2P node. This just communicates with other nodes. It builds a large address book. And then when you're starting up a new node, you just, instead of trying to get the addresses of 10, 15, 20 nodes, you just say, hey, I want to connect to this seed node, and then he's going to give me 10, 20, 50 addresses to connect to in the network. And then you have full nodes. So a full node is just a node that has the full state of the blockchain, either pruned or unpruned. Pruned is just to help decrease the amount of state that you're using on your disk. A normal full node won't have this. And then you have sentry nodes. So, and then I'll touch on this on the next slide. But then you have validators. Validators are just block proposers, and they finalize state. And so we in Tendermint as a round robin, and so it's actually deterministic who will be the next validator. We chose in Tendermint and to design the decisions, it's always meant to be simplicity first. Get it working well, and then work on different iterations. This is something that we worked on, and it's helped us and helped the community that uses Tendermint to be able to get off the ground very fast.
Okay, so it's deterministic who's going to be the validator?
Who's going to be the next
Because in the Ethereum community there was this discussion where they wanted to introduce like a random element. Who will the validator is going to be, because so it's not like that.
So that's actually something that we're going to work on in the next coming months, but it's a very hard problem to solve, and also based on which random beacon you want to use. So there's actually a fork of Tendermint built by the D-Gaming guys, and they introduced a BLS random beacon, and so their validator, the choosing of validators is entirely random, based on their BLS random beacon. And so they introduced BLS signatures into Tendermint. And so this is just another thing that people kind of fork the code base. This is a good place to start. We don't have to rewrite everything. And then we just want to add randomness into the protocol. And since their protocol, their version of Tendermint is primarily aimed at gaming, they have a need for randomness. While in the current version of Tendermint, there isn't a great need for randomness currently. And so, of course, it introduces a tag vector of being able to see, being able to calculate who will the next block proposer be, and then I can go and try and censor transactions, or I can go and try and DOS him and stuff like that. And so for that, we kind of, let me just see which, okay. So, so that's why it's kind of like you have a sentry node architecture, and so because you want to protect your validator from being DOSed, and so the idea is that you set up your own firewall of nodes, and then those nodes have a private key associated with them, and then the validator can only communicate with those nodes, and those nodes are participating in consensus, and so they will propagate the messages to the validator. When the validator signs the transaction, assigns the block, the pre-commit and the pre-vote, then he will send it to the sentry directly, and the sentry will propagate it through gossip throughout the entire network. And so it's kind of like a node of validators. A firewall of nodes. That's kind of the idea behind it, because of this entire being able to deterministically figure out who the next validator is. But also because you don't want someone to just go to the network and try and take down all the validators, because then you kind of stall the network. So this is the Tendermint stack essentially. In this example we're using here, you see my mouse? Yes, you do. Here's kind of the Cosmos SDK. So you have the RPC, so people can communicate with, get health information, send transactions directly to Tendermint instead of the application in byte form. And then if your node is a validator, you most likely have a kind of a key management system, because you don't want your validator to have your key, and then you want to try and set up redundancy. But of course, it's entirely up to the validator on how they want to configure. And then here you have the P2P network, and the P2P network is a gossip-based network. And so everything is kind of sent to everyone. There's no direct communication between nodes. There's no topology of where to send messages. Since it's not a shared blockchain, then we don't have to worry about these things. And then the Cosmos SDK, as we'll see tomorrow in the workshop, exposes also a REST API. So in Ethereum smart contract world, you kind of interact with the smart contract with Web3.js over port 8545. In the SDK's world, you interact with the blockchain just the same way you interact with any backend service. There's exposes a REST API, and you just write to the REST API the same as any other. So now we're going to go over sync protocols, and we'll start with fast sync, then state sync, and then the consensus syncing. So in fast sync, if you're a new chain that's joining the network, you don't want to just go slowly through all the blocks. You want to be able to try and catch up to the current block as fast as possible. And so here, you're validating, you're getting the block sent to you, you're running through the block, verifying the transactions, producing the app hash, making sure it matches the app hash that was sent to you, and then going to the next block. In this case, it's quite a bit quicker than most networks who are just kind of running slowly through the blocks to try and catch up. And so you can catch up with a network that has a couple million blocks quite quickly. But of course, the big question here is, as blocks grow, your state grows, and sometimes you don't even want to hold all the previous state. You just want to be you just want to have the most recent state, and then also being able to participate in consensus, you just want to have the most recent, let's say, 100 blocks. And so this is where state sync comes into effect. So essentially you have Genesis, and then the other nodes in the network start sending you chunks of data. And these chunks you will build into blocks. So you can essentially go from the Genesis block to the 100th, let's say if it's 100,000, you can go to 99,800 and then start fast sync from a closer area. So if you have 3 million blocks and it may take you 3 days to sync, with state sync you can just jump to 2,900,000 and then just sync 100,000 blocks to just get the most recent state. And so in this case it helps speed up things, but then also in the database you're not keeping the last X amount of blocks. And so then when you're caught up to the most recent block, then you switch over into consensus. The main reason why all nodes participate in consensus is because essentially of this century architecture. If nodes were able to connect to each other directly, then not all nodes would have to participate in consensus, because the consensus messages are sent to the validators, and then just the other nodes are just kind of picking up the state after it's been produced. While in a gossip network and a protected public network, then you want a firewall and you need other nodes to participate in consensus so they can send the consensus messages around that will be signed by the validator, and then they'll be propagated everywhere else, and you'll be able to move on to the next block. And so this is kind of the big question. In the case, so there was another sync protocol that was kind of written and they tried to add it to the Tendermint code base, and it was called Hot Sync. And the Binance people actually wrote it, and their idea is the topology of the network is the validators connect directly to each other, and then all the other nodes don't really have to participate in consensus. They don't have to propagate these consensus messages. And so essentially you're running more or less a private network, because if you're kind of exposing your validators to other validators, that means they're exposed to the network, or you guys know each other, and then you're more prone to attack. So here, light clients are kind of the most important thing, and this is something that we've been focusing on the last couple of months, primarily because of IBC and the communication between chains. But on top of that, if you're working off a phone, off a browser, or a laptop, you don't want to sync the entire chain. You just want to be able to get data and write data when you want. And so in this case, you have the idea of a light client. And there's a lot of areas of improvement being worked on here, but the main thing is if you're running a blockchain and you have people in rural Africa or just people with cell phones, or you're an application that you want to trust the network, but you don't want to write your data to a node, because if similar to Infura, most likely if you worked with Ethereum, you've worked with Infura, you're kind of placing your trust in Infura that they're actually propagating your data to the network. They could just be hiding it and giving you back a 200 response, and you could never know better. In this case, you're running essentially your own node that doesn't have the entire state, it only has the state, but you can query full nodes in the network to be able to receive the state that your application is looking for. And so this is what IBC uses essentially to verify that the other chain is has produced and has had the correct state transition in order for the token or data, arbitrary data, to be transitioned to a different chain.
But can light clients count on nodes actually accepting their queries? Like the problem in Ethereum is what? Is that, strictly speaking, if I am running a node, I can choose not to respond to you. And that's why people end up using Infura.
Yeah.
Does this problem exist then?
Yes, so this problem exists with all light clients actually. There's a couple teams working on incentivizing full nodes to provide data to light clients. And so kind of the economic model begins to shift. You need to incentivize people to be able to provide that data to the light clients that are searching. There's one company called Silo, and they built a whole incentivization scheme for full nodes that will communicate data to light clients. Mm-hmm. And so this is kind of a whole new thing. It's also similar to like state sync. When you run with state sync, an entire network starts dropping the previous 100,000 blocks, then you kind of run into a data availability problem, because the last 100,000 blocks could essentially just disappear. An example is Ethereum. If you want to sync a true full node, an archive node of Ethereum, it's going to take you a couple months, not because of how many blocks there are, but because there's only about 3 nodes in the entire network that have the actual full state. And if those nodes were to go down,
and that allow you to
all those
get
blocks,
data from them.
Yeah, all those blocks in the past are essentially gone. Like, you can get them from a database, but the question then is, do you trust that database? Mm-hmm. And so you kind of run into these data availability issues for state sync, and light client, you need to incentivize people to actually provide the correct data, and also ensure that you're on the right chain. The thing here is, if you're a light client that's been in existence, in Tendermint's case, there's an unbonding period for validators. And so if you want to get out of the validator set, you actually have to say, I want to leave, and then there's a 3-week waiting period. It's dynamic in Tendermint, it's up to the application. But in the Cosmos Hub case, there's a 3-week. So if there's a fault that happens because of that validator within those 3 weeks, then they can slash that validator.
What would be nice is for someone to be eligible to be your validator, he must be nice in letting people connecting to him.
I mean,
that would be a good way.
But I do agree with that. But then the problem comes in that you're exposing your validator to the public network, and then essentially they could take down your node, and then you end up getting slashed.
Mm-hmm. And so then perhaps you could have a pair. So you have a light client which is associated with the validator.
Mm-hmm. Yeah. So it's like, but then it's like you're providing that as a service, and then if someone else is using it, then it's like you're trusting that person for that service. And so, I mean, to go fully trustless, then it's very hard. And of course, many applications aren't worried about this. They're worried about users and usability and building a better product.
Yeah, but the Infura is a real problem.
Infura
is in the Ethereum community, it's like it's always problem. So it's a real problem with centralization. So
yeah,
solutions to it.
Ethereum has some light client. Radian is working on some light client stuff. Suma. The nice thing about proof of work, it's easy to verify. The only thing is like you have to wait X amount of blocks, and it's like the more blocks you wait, the more secure, the more finalized your transaction becomes. But yeah, everyone just kind of the easiest thing to do is on IDE is just say connect to Infura at 8545 and then just work from there. And it's also expensive to run an entire Ethereum node. So there's very many trade-offs. I believe I was talking about the unbonding period. So if you're a new light client that joins in, then the problem is that you could actually be fed wrong information that essentially says that you're going to connect to this chain, and this node, this validator, who's feeding you the information can say whatever he wants. And so you need to develop the light client in a way so you can find through the entire network what is the true state, what is the true blockchain, and the state of the application. And so in terms of light clients, usually they try and connect to many nodes so they can verify that the state that they're receiving from one node is the same state that they're receiving from a different node. And then of course, then you need to introduce evidence. So as you try to solve many of these problems, you introduce more problems that you need to solve before you can get all the way there. So this kind of goes back to validators. They're block proposers, and this is kind of a different photo of what would be a century architecture. This is how I want to say 90% of the networks today, Polkadot, Kusama, Silo, Near, all these networks are running. I apologize for the dark. Okay, actually on this screen it looks better. But essentially you have a full node here, a full node, and then they can communicate with each other. So they're persistent peers to each other. But it's either one or all the nodes have one private peer that is the validator. And so this is essentially, here's the network where you're running the blockchain, where the gossip network is happening. And then once it needs to go to the validator, it comes to these nodes and then gets sent to the validator. So essentially your validator can have, it's recommended 1 to 2 to 4, 2 to 3 nodes, and then your sentries can have as many nodes as they want to connect to. And then of course, the simplest way here would be that one of these nodes is a seed node, and so essentially you don't have to connect these nodes to the outside network. You can just connect these nodes to the seed node, and then the seed node will provide you an address book of the entire network. There's some teams working on virtual HSMs in turn, which the idea there, it's kind of scary to think about it, but you can run 3, essentially would be a century node as full validators in the network, and then this HSM is just sitting behind them and saying, okay, I'm going to use this node as the validator to sign this block, and then when I see the traffic increase on him, I'm just going to take the key from him and send it to a different node. And this is kind of scary for many people, but there's a few teams working on it, there are a few teams running on it in production, and it seems to be going well, so it's kind of a new era for validating blockchains. So Tendermint, the design choices for Tendermint Core, the repo, it's built in a fully modular aspect. So you could actually replace the mempool. You could replace, there's a team out there who actually wants to replace the P2P layer with Bluetooth, TCP, and radio. And so it's like, it kind of chooses depending on what's best in its area to use. You can replace the consensus algorithm. So right now, the reason why I'm kind of reading more into consensus algorithm is because I want to try and develop something to put into Tendermint. So to try and do a hybrid consensus or something like hot stuff where you add another round and then you get a fully responsive network. And then you have 2 kind of definitions for a module within the Tendermint codebase. You have a reactor and a module. A reactor is a module that participates and has association with peers. And so like the mempool needs access to the P2P layer to communicate transactions so the next block proposer can get the transactions that need to be in the next block. Evidence, consensus, of course. Tendermint, another, to go back to why we chose to do just a simple round robin, is simplicity. Simplicity is kind of the one idea behind Tendermint and the SDK. We don't want to develop something that's uber complex and super abstracted to the user that, okay, it's easy to write one page of code, but then you don't really know what's going on behind the scenes. We want to engage the user, engage the developer so they know what's going on behind the scenes, but develop it in a simple way so it doesn't take months to understand. It's just you can kind of sit down, see where to start, and you're able to go from there. Now the configurability of Tendermint is the reason why we're not able to get a full test suite within Tendermint for all these different configurations is that you can change the block size, you can change the transaction size. Right, the defaults are what used on the Cosmos Hub, but there's a team who developed a WASM VM on top of Tendermint, and they needed larger transaction sizes, and they just changed one number, and they got larger transaction sizes. And so it's entirely open and free to what you can do and how big you want or how small you want different aspects of the blockchain. So I think I have a lot more time. I actually don't know. But extra section is kind of like interoperability. You can ask questions on IBC and interoperability. This was kind of just like I wanted to talk about what interoperability actually means and can mean in the blockchain space. So for a state machine, it can mean safety and security. So within safety, you can provide data to different blockchains. Security, you can use the Ethereum main chain to validate your chain. So something that we were talking on the idea of burner chains is the problem with application-specific blockchains is you have to worry about your security. But what if you were to build an application-specific blockchain that said, okay, I produce a block, and now I want my validator, who is the Ethereum mainnet, to validate this block. And so I just send the hash of the data to Ethereum, and then in a smart contract there, I say, okay, this is the transaction that I want in Ethereum. It does the transaction, sends it back to the block, to the application-specific chain, and then you're kind of like, okay, you have one validator, but your economic security is the economic security of the entire Ethereum chain. You can do the same thing with Bitcoin as well. And so it kind of opens up a whole different world of how to run your own application with different security models. And then of course the private to public world. You guys went over Hyperledger recently. The biggest thing there is they're a private blockchain. With Tendermint, you're kind of private till you take it public. But with IBC, you don't even have to really take it public. You can run an entirely private blockchain and then communicate through a hub. There's a hub that's recently started. They want to be like an enterprise hub to communicate for enterprise blockchains into the Cosmos ecosystem. And so it kind of opens up that world that you don't have to go through a third party. You can just go through a trustless party who's able to say, for this amount of this transaction, for this transaction, this company has X amount of value to them. Like let's say Novartis has billions of dollars on an internal blockchain, but they want to do something with Ethereum. This blockchain can say like, okay, for this transaction is worth this much, this chain has to have this much economic security. And then what we touched on earlier of non-blockchain machines to blockchain, oracles is one simple example of it, but there's a whole kind of new world to explore from non-blockchain to blockchain. And it also kind of brings blockchain outside of the limelight of it's a back-end technology. And then sharded communications. So a lot of the topology of sharding communications in ETH 2.0, Near protocol and Polkadot Kusama is they kind of all share a similar interface. And so to integrate IBC or something like that, you're essentially integrating communication between shards, but also integrating communication through the entire ecosystem. And with the entire ecosystem, it's like you kind of have growth. And now with these new projects, there's so many blockchains out there. The biggest problem for them is how will they grow a community? And for them to be able to communicate with other chains, they instantly get a larger group. And so the thing for us at Cosmos is we're also interested in growing Cosmos, but we're also interested in growing just the blockchain itself, like the blockchain ecosystem itself. And so that's something that kind of, I guess, sets us a bit separate from everyone trying to say, like, come to our blockchain, come to our blockchain. Our thing is just use something that we can all communicate with. And so, yeah, you get to grow by communicating. And so this is kind of what a simple IBC we'll try and do this essentially later this week, but let's say if everyone's running Tendermint core, you can just communicate the Cosmos Hub, Binance, Ethermint, Cosmosm, and your application. It's quite simple since we all share the same consensus in networking. It's very simple to communicate because then that means we all share the same mic client. And so then it's very simple to communicate with each other. This can be anything. You could essentially move Binance up here and Cosmos Hub here, and then there's also a chance that the Cosmos Hub won't actually be a hub for routing traffic. It may be a hub to communicate to Zcash or Binance, or Zcash, Bitcoin, and Ethereum. Since IBC isn't here yet, we still don't know the full extent of what it will bring. And then this is kind of the ecosystem landscape. With Tendermint, on the Tendermint side, if you include the Cosmos projects, there's about 70 projects who are using Tendermint either in testnet or mainnet. Some of the most notable are Crypto.com, Hyperledger Burrow uses Tendermint, BigChainDB, and Cosmos. Oasis, there's quite a few. Dash, if you've heard of Dash, they're thinking about using Tendermint as a secondary consensus in their protocol. And then, of course, on the SDK, Binance, Paragon, Kava is kind of like MakerDAO, but it has its own chain and it already communicates with Bitcoin, I believe. eMoney, they just received their banking license for the EU, and they're running on the SDK. Sentinel is a decentralized VPN, where you just kind of get the token and you just have a VPN that's being run and verified on the blockchain. Terra is kind of like the most interesting project in a way because they have roughly 900,000 users, but the reason why they're so big, they're in Asia, is that they built an application that has users and has a large user base because the end user doesn't actually know that they're using blockchain. The interesting thing of how they do it is actually they have a decentralized validator set, but the application side of things, they host, and then when they need to put transactions on the blockchain, they just send a batch transaction of all of these transactions onto the blockchain, they get verified, and then the user receives a confirmation that all of these transactions happened. And so there's a few use cases like that where it's actually being used by not people only in crypto, only in blockchain, but by the larger community. And then Cosmos. Any questions? I'm not sure if I went fast or slow through that.
So how does inter-blockchain communication work from the perspective of, does it require an external relayer to query different chains? And
yeah, so in the example that we will be working on, it's just directly chain to chain. But in the future, like you can do chain to chain directly, but you may want to go to a relayer. So some blockchains don't want to run the other blockchains like client, and so the relayer can verify on both sides, relay the information from blockchain A to B, and then back from B to A, saying like, hey, they received it. Now they will act on it and stuff like that. So it's kind of you can kind of go both ways. I believe what is recommended now is to do the relayer, but there isn't a spec for the relayer, as they may be different for every blockchain, for every communication, and so it's kind of.
There's also a lot of talk around incentivization for relayers.
Mm-hmm.
So right now, the first and simplest version is just no incentive, but the same way that Ethereum meta transactions have incentives built in sometimes, but they don't have to. It's sort of like at a level above the protocol.
Like the same way validators are now making money from running and securing networks, a relayer could be a secondary business model for validators or for wallets. Wallets can run their own relayers, and kind of you're essentially just building out business models for supporting the whole ecosystem. break and then come back, and I think then we have one of
You ready to the next one?
Yeah.
Cool.
Yeah.
so the next one's on Golang. So it's a bit of programming. So that's the fun part.
15 minutes.